Welcome back, everyone. Today we practice more with the notion of factorial, which we introduced in the second episode of this season. Let's recall how the factorial came about. Remember this problem about the line of people that are formed in front of the border control? How many lines or how many ways are there possible to form a line from the n people? Generally, a permutation of n objects, for example, of n people in front of the border control, is any ordered arrangement of them. Any arrangement, let's say Mike is first and Alisa is second and Joy is last, and so on and so forth. Any such arrangement is called a permutation, and the number of all permutations, as we computed during that episode, is 1 times 2 times 3, etc., up to n, the product of all numbers between 1 and n. That's denoted by n with an exclamation mark, and is called n factorial. Let's practice more with the notion of factorial. How many different words can be made by rearranging the letters of the word doctor? There are 1, 2, 3, 4, 5, 6 letters total. So a naive answer would be 6 factorial. Any permutation of the 6 letters leads to a different word with or without meaning. The meaning doesn't matter here. And so 6 factorial would be the answer, but that's not right. And it is not right because there are repeated letters here. The 2 letters O are the same. Imagine what happens if we flip the 2 letters O. Just flipping the 2 O's does not lead to a new word. It's an identical word. But we counted it as a different permutation. We did it for every permutation. We counted every permutation twice. And that's why 6 factorial leads to an overcounting of the actual number of permutation by a factor of 2. We overcounted twice. How do we correct that? Well, since we know we counted every permutation twice and we shouldn't have, we just, to get the right answer, just divide by 2. This is all permutations of 6 letters, thinking that the letters are different. And this is the overcounting correction, in which we ignore the order of the 2 letters O. So this is the correct answer, 6 factorial divided by 2. And this is 1, 2, 3, 4, 5, 6 divided by 2. 2 cancels, and we get 360 as our answer. Another example. Let's repeat this same problem for the word success. There are 7 letters in this word. So the naive answer to this problem would be 7 factorial. However, as before, we have two repeated letters C here. So every permutation in which the letters C are flipped is counted as a different permutation, but it shouldn't have, because it's the same word. To overcount for the to correct for this overcounting, we divide by 2. That's actually indicated by 2 factorial here, because 2 factorial is how many ways you can flip the 2 together. And we also have 3 letters S that are identical. By how much did we overcount because of the repeated letter S? Well, if we rearrange the letters S within themselves, that will lead to the same word, so we should count it as one word. But how many rearrangements of 3 letters are there? There are 3 factorial of them. So every permutation, every word, we counted 3 factorial times, and we shouldn't have. So to correct that, we divide by 3 factorials. 3 factorial. Again, this is all permutations of 7 letters, as if all the 7 are different. And here we are ignoring the order of C's, of the 2 C's. And thus we do the overcounting correction. And here we're ignoring the order of 3 S's. And again, we do the overcounting correction. The answer is 420. And here's one more problem. Suppose Alisa has 7 friends and she wants to invite 3 of them for a party. In how many ways can she do that? In how many ways can Alisa invite 3 friends from her 7 friends that she has for her party? Here is how we can think conveniently about this problem. Imagine yourself being Alisa. You would like to make an invitation list of the friends. And here's how the invitation list generally looks like. You put down your friends, suppose just call them A, B, C, D, E, F, G, H. 4, 5, 6, 7, just G. 7 friends. And next to each friend, you want to put a mark, invited or not invited. For instance, friend A, no, let's not invite that friend. Friend B, yes. C, no, not invited. D is not invited. E is, oh yeah, let's maybe E is your favorite friend. Let's invite E. And F is not invited, and G is, yeah, let's invite G. In this way, Alisa invited her friends B, E, and G. 3, she chose these 3 friends. Every invitation, any invitation list Alisa can possibly make will look like that one. And we can think of an invitation list now as a word, as a 7-letter word made up of 2 letters, Y and N. How many number of such words are there? How many such words are there? We solved that problem before. There are 7 letters here, so 7 factorial would be the naive answer. That's how many words are there if all letters were different, but we overcounted. We should ignore the order among the Y's And there are 3 factorial possible reordering of y's. And we should also ignore the order among the n's. And there are 4 factorial possible reordering of the 4 letters n. Ignoring the order of y's and n's leads us to the answer 35. There are 35 ways Alisa can invite 3 from her 7 friends for her party. Let's discover an alternative and a more direct solution to the same problem. Again, imagine yourself being Alisa. What would you do to invite the friends? You would decide who are you going to mail the invitation to first, who are you going to mail the invitation second, and who will you mail the invitation third. So we are trying to compute the number of ways to invite the 7 friends, to invite 3 friends out of 7. You're going to decide who are you mailing the invitation first. Well, how many ways are there to choose? There are 7 friends. There are 7 ways to mail the first invitation. After you have done that, you want to mail the second invitation. How many ways are there to do that? There are 6 ways to do that. You're not going to invite your first friend twice. 6 ways to mail the invitation, to mail the second invitation. And after you mail the first 2 invitations, there's 1 more friend to invite, and there are 5 remaining ones. So there's 5 ways to invite, to mail the third invitation, to choose who you want to invite third. 6 times 7 times 5. Is this the answer to the problem? No, it can't be. The true answer is 35, and this number is bigger than 35. So it's not the same. What did we do wrong in the second solution? Where did we slip? We overcounted. Why? Because we thought it is important in which order the invitations are being sent. In this particular case, Alisa invited friends B, E, and G, and it was important that, let's say, E gets the first invitation and G gets the second, and maybe Y gets the third. But it could have been different. Just the same friends could be invited in a different order. Maybe B got invited first, and E gonna be invited second, and G is invited third, or something else. In other words, this answer would be correct if the order of invitations mailed is important. But in this problem, the order is not important. It's just important who the friends are that get invited. And so what we have to do is we have to correct this solution, have to correct the overcounting. How much did we overcount? Well, obviously we overcounted by 3 factorial. This is how many possible reorderings of invitations there are. Divided by 3 factorial. And let's check that this is correct. This is 7, 6, 5. And to make a factorial appear on the top, let's pretend that we're counting down, that we're multiplying by further numbers here. And let's correct that so we cancel these numbers in the bottom like this. This allows us to write this as 7 factorial on the top, 3 factorial times 4 factorial on the bottom. And now we're happy because now we got the same answer. Now we're good. We corrected our solution and it's the same answer. This problem is one of the many examples of similar problems appearing in life, in science. It is so important that it has a name. more generally, let's say, number of ways to choose k objects, let's say 3 friends in that example, from n objects in any order, the order doesn't matter. The number of ways to choose k objects from n objects. Let's just redo the same problem, but with general n and k. What it's going to be, it is n factorial on the top, just for the same reason, divided by, and now the correction comes, divided by k factorial, that's that, and further divided by n minus k factorial. That was 4 factorial in the previous example. Stop for a moment, think about this. Just redo this problem for general k and n, and you will see that this expression arises as the answer. It is very important, and it has a name. It's called a combination. By definition, a combination is any way to choose an unordered subset of k objects, such as unordered subset of 3 friends, from a set of n objects, such as 7 friends. The number of all combinations as we discovered equals n factorial divided by k factorial and further divided by n minus k factorial. This number is denoted this way, is pronounced n choose k, and is called the binomial coefficient, for the reason that will be clear later. In our particular example, the number of ways to choose 3 friends from 7 friends, as we computed in this notation, is 7 choose 3. We're choosing 3 from 7. Thus, 7 choose 3, and we computed it was 35. It is a good time to review this definition because it is extremely important for the rest of this class and for many areas of mathematics. So please let it soak in, the definition of combination and the definition of binomial coefficient. Play with it a little bit. Memorize it, this formula. And we'll see you in the next episode. Stay with me.